Something happens when the moon slides between you and every other human being who has ever lived. The radio goes quiet, not like a bad signal, quiet like the universe itself decided to stop listening. No static, no hiss, just nothing. A silence so complete it has a physical weight to it. For the Artemis 2 crew, that moment is not hypothetical. It's scheduled. It's in the flight plan. And when it arrives, Mission Control in Houston won't be able to help them. Not because the engineers aren't trying, because the laws of physics won't allow it. This is not a story about everything that could go wrong in space. This is a story about the one thing that makes everything else harder, the silence, and why the most sophisticated crewed spacecraft ever built cannot escape it, cannot negotiate with it, cannot engineer around it. This is the Orion Survival Trap, and it starts with the speed of light. The speed of light is 186,282 miles per second. That number sounds like an asset. In deep space, it is a liability. When Orion is in low Earth orbit, the communication delay between the spacecraft and Houston is essentially zero. A fraction of a second. Imperceptible. The astronauts aboard the International Space Station talk to the ground the way you'd talk to someone in the next room. The feedback loop is intact. The safety net is live. Then they leave low Earth orbit and the numbers change. At the average distance of the moon, roughly 239,000 miles from Earth, a signal traveling at the speed of light takes 1.3 seconds to arrive. One way. That means 1.3 seconds there, 1.3 seconds back. A 2.6 second round trip for every single exchange. Every question, every answer, every warning. 2.5 seconds doesn't sound catastrophic. For routine status checks and scheduled reports, it isn't. But emergencies don't schedule themselves, and emergencies don't wait 2.6 seconds to become unrecoverable. There is a threshold that engineers quietly call the lag wall. Below it, real-time collaboration between crew and ground is genuinely possible. Ground sees something anomalous and the telemetry flags it, the crew responds, mission control confirms. The loop closes in seconds and the problem gets caught before it escalates. Above the lag wall, the loop breaks. Mission control shifts from active problem solvers to something closer to informed spectators. They can send recommendations, they can analyze the data they receive, but by the time their advice travels to the crew and the crew's response travels back, the situation on the spacecraft has already moved on, resolved or unresolved without them. Artemis 2's trajectory carries Orion out to approximately 4,600 miles beyond the lunar surface at closest approach, and swings it to a peak distance of roughly 252,757 miles from Earth, farther than any human has traveled in history. Apollo 13 hit the lag wall in a crisis. The oxygen tank exploded 205,000 miles from Earth. The round-trip delay was about 2.3 seconds. Ground controllers worked furiously and brilliantly, and they saved those 3 men. But the crew was also improvising in real time, making decisions faster than Houston could track. The gap was already there, even on that relatively short mission. For Mars, the lag wall becomes a canyon. At average Mars distance, the communication delay runs around 20 minutes each way, 40 minutes round trip. If something goes catastrophically wrong on the Martian surface and the crew sends a distress signal, by the time Houston receives it, processes it, and transmits a response, 40 minutes have passed. The crew has either solved it or they haven't. The answer from Earth arrives either way. Artemis is the bridge between where we are and where that scenario leads, and bridges by definition have to cross a gap. This one is measured in light seconds, and the gap is getting wider. There is a place behind the moon where nothing works. Not because of equipment failure, not because of solar interference, because the moon itself is in the way. 2,159 miles of ancient rock sitting between the spacecraft and every radio telescope, relay satellite, and communication antenna on Earth. Radio waves do not bend around planetary bodies. They travel in straight lines at the speed of light, and if something solid is in the way, they stop. The moon puts a wall between Orion and Earth that no current technology can penetrate. For approximately 40 minutes during Artemis 2's closest approach to the moon, The crew will experience complete communication blackout. No voice link to Houston, no telemetry stream, no data in either direction. The spacecraft's computers will continue running. The life support will continue processing. The crew will continue breathing, but from Mission Control's perspective, Orion will simply vanish. The telemetry will freeze on their screens mid-value, and the room will wait. Apollo crews knew this silence. Every mission that reached the moon passed through it. When Michael Collins orbited alone in the command module during Apollo 11, while Armstrong and Aldrin walked the surface, he spent 48 minutes of each orbit completely out of contact. He later wrote that he was aware, in a way that was almost abstract, that he was the most isolated human being in the history of the species. More alone than any castaway, more alone than any prisoner in solitary confinement, alone on a truly cosmic scale. But Apollo crews were on missions measured in days. The blackout was a passage, a known interval with a defined end. The spacecraft would reappear on the near side, comm would be reestablished, and the mission would continue. The Lunar Gateway, the planned space station that will orbit the moon and serve as a staging point for surface operations, is designed partly as a communication relay, but near constant is not the same as constant. There are orbital geometries where the relay isn't ideally positioned, coverage gaps, and on the lunar surface itself, operations near the far side or inside permanently shadowed polar craters will face blackout windows that can stretch from minutes into hours. The relay satellite constellation that could theoretically eliminate those gaps doesn't fully exist yet. Right now, today, if something goes wrong in the shadow zone, a pressure anomaly, a fire, a medical emergency, a system cascade, the crew is unreachable. Not inconveniently unreachable, irretrievably unreachable for the duration of the blackout. That is 40 minutes during which Mission Control has no information, no ability to assist, and no way to know if the crew is coping or dying until the signal reappears on the other side of the moon. The shadow zone doesn't move. It doesn't shrink as technology improves. It is a geometric consequence of flying behind a 2,159-mile body that blocks all electromagnetic signals. The only way around it is a relay on the other side, and for now, that relay isn't there. Every crew that passes through the shadow zone has to be prepared for what it means, that for some number of minutes, they are it. The last line of decision-making, the last pair of hands that can touch anything that matters. For 60 years, human spaceflight has operated on an assumption so fundamental it is rarely stated out loud. Someone on the ground is watching. Mission Control is not just a support function, it is a redundancy system. Every astronaut flying in space has, in a practical and immediate sense, an entire building full of engineers looking over their shoulder in real time. When something anomalous appears on a display, the crew reports it. The telemetry simultaneously arrives in Houston. Specialists cross-reference it, and within seconds, sometimes faster than the crew's own assessment, an answer comes back. The loop is tight. The safety net is live. The margin between a problem and a catastrophe is filled with human expertise on the ground. That system saved Apollo 13. It saved Columbia's crew from a worse outcome during STS-1 when tile damage was caught on ascent imagery. It has saved lives in space routinely, invisibly, in ways that never become famous because the problems get resolved before they become disasters. Deep space kills that system, not all at once, not dramatically, progressively. As distance grows and the lag compounds, Mission Control transitions from a real-time safety net into something closer to a very well-informed correspondent. One who can offer excellent advice but can't guarantee it arrives before the situation has already resolved itself. Orion was engineered with this future in mind. It runs 4 independent flight computers in parallel. It can, in principle, fly itself. It proved that on Artemis 1 in 2022, when the uncrewed spacecraft completed a full lunar mission autonomously from launch through lunar orbit, through re-entry, and splashdown without a human hand touching a control. But software doesn't know what it doesn't know. The failure modes that have killed people in space have consistently been ones that were technically within the system's awareness, but fell outside the decision-making loop at the critical moment. Challenger's O-ring problem was documented before launch. Columbia's foam strike was visible in ascent imagery. Apollo 13's oxygen tank had anomalous behavior in pre-flight testing. In every case, the information existed. The question was whether anyone or anything would recognize its significance before it was too late. Orion's onboard AI can detect sensor anomalies and execute pre-programmed contingency responses. It can reconfigure systems, redistribute power, and initiate abort procedures. What it cannot do is exercise judgment, look at a situation that doesn't quite match any pattern in its training data, recognize that something is wrong in a way the models didn't anticipate, and improvise a response that isn't in the playbook. The crew can, which is precisely why Artemis II has spent portions of the mission performing manual piloting demonstrations, physically flying the spacecraft through deep space, testing different control modes, evaluating how Orion responds when a human is actively directing it, rather than letting the computers run autonomously. The Artemis II crew is being asked to develop a capability that Apollo crews never needed and never trained for: the ability to operate the spacecraft independently without real-time ground support in scenarios that weren't in the original mission plan. Apollo astronauts were extraordinary test pilots, but they flew manually during specific anticipated phases: docking, lunar descent, landing. The command module itself was never intended to be flown through open space by hand in a contingency. Mission control was the contingency. The ground was the backup system. The new architecture assumes the ground might be unreachable, and it asks the crew to fill the space where mission control used to be. This is the autonomy trap. Not that the technology has failed, it hasn't. The technology has advanced to the point where it can keep 4 people alive 250,000 miles from Earth in a capsule the size of a walk-in closet, transmitting high-resolution video home via laser at speeds that would have seemed impossible in 1972. The trap is that the distance those systems make survivable is also the distance at which the most important safety system in the history of spaceflight, the one staffed by hundreds of humans in a room in Houston, goes dark. The spacecraft is better than it has ever been. The distance is longer than it has ever been. The gap between those two facts is where the crew has to live. There is a phenomenon that happens to astronauts in the first hours after reaching orbit. They float to the window. They look down at Earth, and something in their perception permanently shifts. The overview effect, documented by writer Frank White after interviewing dozens of astronauts across several decades, is one of the most consistently reported experiences in the history of human spaceflight. The sense of scale, the fragility of the atmosphere, a paper-thin blue arc against absolute black, the invisible borders of every nation that has ever gone to war, the recognition that everything human beings have done, every building and road and buried city and ocean voyage, exists on the curved surface of that pale sphere. Now imagine the opposite happening. Imagine watching that sphere shrink. The Earth doesn't disappear all at once. It diminishes incrementally over hours as the spacecraft accelerates away. At 10,000 miles, you can cover it with your thumb. At 100,000 miles, it is a bright blue marble smaller than the full moon looks from Earth's surface. At 250,000 miles, it is a point of light, recognizable if you know where to look, but distant in a way that is felt, not just understood intellectually. And behind the moon, it disappears entirely. The Artemis II crew is being monitored more comprehensively than any deep space crew in history. Sleep patterns tracked via wearables, cardiovascular data logged continuously, cognitive performance assessments administered at regular intervals, radiation dosimetry recorded at multiple points on and inside the capsule. All of it is being stored in real time to be analyzed against pre-flight baselines in the weeks and months after splashdown. What the research already tells us is sobering. Isolation, even partial isolation, even monitored isolation, degrades human performance in ways that are not always visible to the isolated individual. Cognitive processing slows. Risk tolerance increases as executive function is taxed by sustained low-grade stress. Interpersonal friction in small, confined groups accumulates over time in ways that accelerate in the second and third weeks of close confinement. Sleep quality in space is typically poorer than on the ground, even with pharmacological support, because the light environment is wrong, the noise environment is wrong, and the body's circadian rhythms are running against an artificial schedule. And then there is the radiation. Outside Earth's magnetic field, beyond the Van Allen belts that Orion punches through twice on this mission, once outbound and once on the return, the crew is exposed to galactic cosmic radiation and potential solar particle events at intensities that would be considered unacceptable for prolonged occupational exposure on Earth. Apollo crews reported seeing flashes of light with their eyes closed, cosmic rays passing through the vitreous fluid of their eyes and triggering photoreceptors in the retina directly. We now know those same particles were simultaneously passing through the gray matter of their brains. The long-term cognitive effects of deep space radiation exposure are among the most actively researched and least understood problems in human spaceflight medicine. Animal studies suggest that galactic cosmic ray exposure can impair hippocampal neurogenesis, reduce executive function, and increase anxiety-related behavior. Human data from deep space is almost entirely absent. The Apollo program generated some, not enough for statistical significance, not enough to draw confident conclusions. Artemis 2 is generating more. Right now, as the crew performs their duties and sleeps in their bunks and looks out the windows at the shrinking Earth, their biology is being recorded with a fidelity that Apollo never approached. The data from this mission will directly inform the radiation exposure limits, crew selection criteria, and mission duration parameters for every deep space program that follows, including the first Mars mission, which will expose its crew to approximately 18 months of galactic cosmic radiation in transit alone. The human toll of isolation isn't just psychological, it is physiological, it is cumulative. It doesn't announce itself with a warning light or an alarm. It arrives quietly, in the spaces between tasks, in the slight slowing of a decision, in a sleep cycle that doesn't quite restore, in the background hum of a stress response that never fully resolves because the stressor, distance, silence, the absence of Earth, never fully goes away. That is the real challenge of deep space. Not the vacuum outside the hull, not the re-entry plasma, not the rocket equation. The challenge is keeping the human being inside the capsule sharp and functional and psychologically intact in an environment that has no evolutionary precedent, no cultural preparation, and no way to be made to feel like home. In December of 1972, Gene Cernan stood on the lunar surface for the last time. He climbed back into the lunar module and said before sealing the hatch, "We leave as we came, and God willing, as we shall return." It took 53 years. Not because the technology failed, not because the missions had gone badly, because the political will ran out, and the budget ran out, and the public moved on to the next thing. Apollo proved a point. The point was proved, and the program ended with 12 men having walked on another world and no clear plan for what came next. The Artemis program is not a sprint. It is an infrastructure program, slower, more international, more complicated by the coordination overhead of involving partner agencies across Europe, Canada, Japan, and elsewhere. It involves a space station in lunar orbit, a series of increasingly capable surface missions, and an eventual path to Mars that will take decades to execute. There are engineers inside NASA and its partner agencies who believe the communication architecture for Artemis lunar surface operations is insufficient. That placing humans in environments where extended blackout is structurally possible, where the shadow zone exists and no fully operational relay system exists to cover it, represents a risk category that policy acceptance papers over rather than resolves. There are also engineers who believe the current approach is defensible, that the crew's demonstrated autonomous capability is itself a meaningful mitigation, that the history of exploration is a history of proceeding with known limitations and closing them iteratively, rather than waiting for perfection that never arrives on schedule. Both of these positions are coherent. Both are supported by evidence and argued by people who understand the problem deeply. The disagreement isn't between the well-informed and the reckless. It's between people who draw the acceptable risk line in different places using the same data. After Artemis 1 returned in 2022, engineers found unexpected erosion in the heat shield's ablative material. Portions of the shield had charred and flaked off in patterns the thermal models hadn't predicted. The underlying structure held, the interior temperature stayed within limits, but the anomaly raised questions serious enough to convene an independent review team. Some engineers pushed for a redesigned shield before putting humans on top of it. NASA Administrator Jarek Isaacman reviewed the data, met with engineers and external experts, and gave the go-ahead for Artemis 2 with the existing design, with a redesign planned for Artemis 3. The crew knows this. They accepted it. Every astronaut who has ever flown has accepted some version of this bargain. The acknowledgement that the engineering is not perfect, that the margins are real but not infinite, and that the exploration requires a willingness to go anyway, because staying is also a choice with consequences, and waiting forever is its own kind of failure. What was once a last resort, the free return trajectory that saved Apollo 13 after catastrophic failure, is now the primary flight plan for Artemis 2. What was once an emergency is now the architecture. That sentence contains everything you need to understand about what Artemis is and where it is going. The Artemis 2 crew will splash down in the Pacific Ocean around April 11th. Recovery vessels will be positioned. Airbags will inflate to right the capsule if it enters inverted. Divers will approach the popping spacecraft, open the hatch, and help 4 people into the sunlight who will have done something that no human being has done since December 1972. Returned from deep space, alive. The debrief will begin within hours. The data will take months to fully analyze, and then the engineers and flight surgeons and mission planners will sit down together with everything those 4 people experienced, everything the sensors recorded and everything the sensors missed, and use it to determine whether the next step is safe enough to take. That is how exploration has always worked, not in a single decisive leap, in a series of questions, each answered by going, each answer revealing the next question a little further from where you started. The void doesn't negotiate. It sits there 250,000 miles from everything familiar, offering a silence so complete that no technology has ever been able to fill it. 4 people just heard it. They floated behind the moon, past every signal and every voice, into 40 minutes of absolute quiet, and then they came back. Not because it was without risk, because it was necessary. Apollo proved we could leave. Artemis is learning what it costs to stay gone. If you want to know what it exactly feels like to be inside that capsule right now, the food they're eating, how they sleep, what they see through the windows, the moments that no briefing can prepare you for, watch what Artemis 2 astronauts will actually experience. It's right here, and it picks up exactly where this one ends.